Hi, welcome back to Math 533, Topics in Euclidean Geometry. In this video, we're going to be talking about two things, two very closely related things. One of them is called the medial triangle, and that's a way of decomposing a given triangle into smaller triangles that are similar to the big one, so similar to the one you started with. And the other thing we'll talk about is what's called the centroid of a triangle. It's a special point associated to the triangle. It's also sometimes called the center of mass or center of gravity of the triangle. Okay, first up, let's construct something called the medial triangle. So I'm going to take midpoints of each of the sides, and the triangle I get that connects those midpoints is called the medial triangle. And it's an important fact that we talked a little bit on our Zoom meeting last week, that the four triangles you get inside here, so notably the one I have here in blue dashed lines, but also the three that are outside, right, the A, B prime, C prime, A prime, B prime, C, A prime, B, C prime, as well as A prime, B prime, C prime. These four triangles are all congruent to each other, the four small triangles, and they are all similar to the big triangle, and they're all similar with either ratio 2 or ratio 1/2, depending on which order you're saying. They're half the size of the big triangle. So I say triangle ABC is similar to triangle A prime, B prime, C prime with ratio 1/2. If I reverse it and say triangle A prime, B prime, C prime is similar to triangle ABC, I get ratio 2. Okay, another important definition is we say that three lines in the plane are concurrent if all three of them intersect in the same point. Right? Notice that two lines intersect in a point unless they're parallel. So there's nothing interesting about two lines. But in general, three lines, you don't expect them to meet in the same point. You expect them to meet in three different points. And so being concurrent is an interesting property for three lines. On the homework, you proved that the three perpendicular bisectors of a triangle are concurrent, and that intersection point of all three of them is called the circumcenter of the triangle. So now let's introduce something called the medians of a triangle. So if I take my triangle ABC and I construct the midpoint of the opposite side, so in this case, let's say I'm interested in A, then I construct A prime as the midpoint of BC, then the segment AA prime is called the median from A. Obviously, a triangle has three vertices, so it has three medians. And the theorem that we're going to prove is that the medians are concurrent in a point that is called the centroid. And the centroid of the triangle is also the center of gravity or the center of mass of the triangle. I'm pretty sure the G stands for gravity, but whether it stands for it or not, that's a good mnemonic for why people always, or not always, but quite often use G to indicate the centroid of the triangle. And when I say center of mass, I mean if you imagine this thing was made out of some thin material, like a piece of cardboard or something, in principle you'd be able to balance it on a pin located at G. Okay, and the other fact that we have is that the center of mass, the centroid, cuts each of the medians in this 2-to-1 ratio. Right? So it's the ratio of GA over GA prime is 2. And that's true for each of the medians. Okay, so let's go through the proof that the medians are concurrent. And we're going to use a little bit of a roundabout argument here. So first, we're going to look at what happens with two medians. So let's say A prime, and B prime. They intersect in a point. I'm going to name it G. Why not? And that's true because those lines are not parallel. And I'm going to imagine now, to connect A prime and B prime to each other. And if you think about it, we have now this triangle here, C, B prime, A prime. That's similar to my big triangle with ratio, well, either ratio 1/2 or ratio 2, depending on which order I put it in. So the order I put it in, I get ratio 2. The big triangle is twice the lengths of the small triangle. And from this, we get in particular that A prime, B prime is parallel to AB. Right, so my horizontal dotted line here is parallel to this horizontal line at the bottom. And furthermore, the ratio of the sides is that AB is twice the length of A prime, B prime. So now, using alternate interior angles, I guess technically the converse to the alternate interior angle theorem, right? I'm thinking of BB prime, let's say, as one of the transversals, and I have A prime, B prime, and AB as my pair of parallel lines. Then I get these things I have in a single tick mark are a pair of alternate interior angles. Similarly, where I think of A prime as a transversal, I get the double tick marks. And then these red angles here at G are a vertical pair. So we now have two triangles, G A prime B prime and G A B, and they have that corresponding angles are congruent. And therefore, by the angle similarity theorem, those two triangles are congruent to each other. And as we observed before, AB is twice A prime B prime. So that means that the ratio here gives me a factor of 2 between my two triangles. So this tells me that GA is 2 times the distance GA prime. And now doing a little bit of algebra here from the fact that AA prime is AG plus A prime G, I get that AG is 2/3 of the whole distance AA prime. Okay, so now let's see what we can figure out coming from a different pair of medians. So now I'm going to take, for instance, the median AA prime and C prime. Their point of intersection I'm going to call G prime. And our goal here is to show that G prime and G are the same thing. Okay, the same argument as before, right? We look at, we connect A prime, C prime, and we get triangles A prime, C prime, G prime, and ACG, show they're similar, and come up with the fact then that AG prime is 2 times A prime, G prime. Same algebra kind of argument that we did before, to then say that the distance AG prime is 2/3 of the distance from A to A prime. So now we have that AG, right? G is a point on this line AA prime. AG is 2/3 of the way from A to A prime, but also AG prime is 2/3 of the way from A to A prime, and both G and G prime are between A and A prime. So that gives us that G equals G prime, and hence all three medians intersect in the same point, which is both G and G prime. Okay, that's it for this video. Thank you for watching. I hope you enjoyed the medial triangle and the intersections of the medians. I think it's a really pretty construction. I hope you enjoyed it too. Thank you for watching. Happy mathing.